Okay, so we are going to do this question. I found it in the book, and it just reminds it. I don't know. I just think this is going to be on the exam. Look at it. It just looks like an exam question. All right. So it's telling us if f is this, find a function f such that f equals the gradient of f. So we should know by this stage that this statement here basically tells us that f is conservative. So they're basically saying, implicit in the question is, hey, f is conservative, find the potential function. I'm going to prove that this is conservative to start off with, just because, why not? Just for practice. All right, so the first thing that we've got to realize that, let's just say f equals, and let's just replace these values for p and q, right? If this is conservative and therefore f is the gradient, well, the gradient is just the derivative. So this is just telling us that p equals f with respect to x, and it's respect to x because, you know, I is that x component, and it's telling us that q is the derivative of x with respect to y because j is the y component. So that's basically, if this is conservative, these things are true. All right. Now, if we want to verify that this equals this and that this is this, how do we do that? And what we do is we actually take another derivative of f, but now with respect to the opposite variable. So you'd now take the derivative of this with respect to, y, df dx, and you'd take the derivative of this with respect to x. Now, why will you do this? Because if this is conservative, then these should be the same function, and then these two things should equal. This is something called Clauret's theorem, and you've probably run across it a few times. If not, you know, it's a good thing to know. All right, so with all this background, this is all just background to the question. Let's now prove that this and this are conservative. So let p equal, let's get a new color. Let p equal 3 plus 2xy. Therefore, dp dy, yes, dp dy should equal, so we're deriving this with respect to y, so that goes away, and we're just left with 2x. And then we get q is x squared minus 3y squared, and let's derive this with regards to x. So we're doing the opposite one. Do you get what I'm saying? Do you get it? So this is 2x, and look, 2x and 3x means that these two things are equal. 2x and 2x, they're equal. Therefore, this is conservative. So now, we've proved that it's conservative. All right, so now let's find the potential function. How are we going to do that? Well, we have proven that we've proven that d of f of d of x equals this, 3 plus 2xy. That's what we've proven, see? P equals this. This is P, therefore this is that, right? So if we now want to find what f is, what do we do? Because we've got the derivative of f with respect to x. So how do we turn this into just f? Well, we integrate it with respect to f. That's why integration is sometimes called anti-differentiation, because it's just the opposite of differentiation. So we're going to get f equals, so we're going to integrate with respect to x, so we're just going to plus, we're going to put an x there, and we're then going to get 2x squared, we're going to add 1 then divide it by that one. So we're going to get f equals 3x plus x squared y. Okay. And then we're going to get a gy. That's our constant. Our constant will be a function of y. That's why we call it gy. All right. So the next thing we want to do now is, what do we want to do next? Well, we've got this. We could turn this into this. We could turn this into df of dy, right? Which is this. Well, it should be. So if we do that, what are we going to get? We're going to get, if we derive that with respect to y, we'll get 3xy. Sorry. We're deriving it with respect to y. So that would go away. This would become x squared. I'm getting mixed up between integration and the other one. And then this one would become plus g derive of y. Right? So then now this is that. Yeah? Do you get that? So we started with df of dx. And that was 3 plus 2x. And we said, hey, if we integrate this with respect to x, we'll get f. And we did. We got f down here. Now we said, hey, we know that q is df dy. Well, we've got f. What if we now derive this by y? So we did that. And we got this. And we go, hey, this should be the same as that. And it is kind of the same. We've got an x here. We've got an x there. Well, what on earth is this? Well, that tells us that I don't like green. That tells us that this must be this. So g of y must be minus 3y squared. So in other words, if we want to get what g is, we have to integrate with respect to y to get rid of that derivative. And we're going to get minus y cubed. All right. So we can say, hey, we have just figured out what g of y is. So we can sub g of y equals this. So we can sub this into here. So our final potential function is going to be f equals 3x plus x, that's about it, plus x squared minus y cubed. And that is what it's going to be. Pretty cool. All right, so that was part A. All right, let's take a breather. Let's rub stuff out. Rub. So we proved that it's conservative. We've proved that. And we found the potential function. So now they're going to tell us to evaluate the line integral this. Let's write that down. Oh, that's laggy. dr, where c is the curve given by 4. Look at that is just horrendous. If you got that in an exam, you would just cry. Be like, just give me the fail. But we're not going to cry because we know what to do. All right. They want us to find the line integral, and they've given us this formula for it, which we've written down here. Now, we proved in the first part of this question that f is conservative. See, f is the gradient. Therefore, we can rewrite this formula like this, d of f dot dr. And this should ring some bells. We should know from the fundamental theorem for line integrals that this is simply, see, I should know this. I'm going to have to look it up. I don't want to write it down wrong. this is f of r of b minus f here being this thing here, of r of a. Alright, so let's just explain something here. We've proved that it's conservative. So that means that our line integral is going to be the same no matter what the curve is. Alright, so here are 2 points. Here are 2 points. See, we're minusing 1 point to the other. Let's say we went from here to here. And let's say then we went from here and we went like this. We got lost for a bit, we didn't know where to go, and then we finally made it. Would you not say that this line would have a smaller value than this line? Well, you'd be wrong. Because it's conservative, the same amount of work has been done, right? The conservative vector field kind of like cancels out the right amount of stuff. I don't know. But all you have to know is that for a conservative function, the curve is irrelevant. We don't even have to know the curve. That's why, you know, they've tried to scare us with this big scary curve here, but we know that it's conservative. So we know that it doesn't really matter what the curve is. All right, so what do we do now? All right, so all we have to do is find the start and end point, and that's pretty easy. We simply plug in, well, we know that the start point is t equals 0. So we'd go r of 0 equals e of 0 sine of 0 I plus e of 0 cos of 0 j. E to the 0 is 1 times sine of 0 is 0 I plus e of 0 is 1 times cos of 0 is 1 j. So that tells us that r of 0 equals 0 for our x and 1 for our y. That's what it tells us. So this is the relevant piece of information. All right, so we can let's rub. Let's rub. All right, so we just found, so this is our smaller function though. So our smaller function is the one that we minus. So we just found this value. This value is this. So we can rewrite f as 0 and 1. We can do that. Let's now find r of b. Well, we know that b, what do we know about b? Where is it? Oh, here it is, pi. Well, we know that r of pi is going to be e of pi sine of pi I plus e of pi cos of pi. Well, that's a horrible S. Absolutely woeful. Cos of pi is j. All right, so e of pi is e of pi. It's just e of pi times sine of pi is 0 plus e of pi is just e of pi and cos of pi is negative 1. So therefore our x value for I on pi is going to be 0 for x and negative pi, negative e on pi. All right, so we can put that in for this, 0 negative e on pi. That's a pi. That's a crazy looking pi. All right. Whew, what a long question. Maybe this is too long for an exam. All right. All right. So we've proved that it's conservative. We've got our potential function. We found our start and end points. And now we just have to go, all right, we have to just sub them in. So here's our f. So we're going to go f of 0 to negative e on pi is going to be, well, we're going to chuck a 0 in there. So we're going to get 3 of 0 plus 0 squared y minus, sorry. Y is going to become negative e on pi minus negative e on pi to the 3. So this is going to go away because this is 0. This has got a 0 in it too, so it's going to go away. And we're going to end up with, these negatives are going to become a positive, so we're going to get e 3 pi. Pretty cool. Pretty cool. And then we're going to do the same thing for our other value, which is 0 and 1. 0 and 1. It's going to be kind of the same. We're going to get 3, 0, plus 0 squared, 1, minus 1 cubed, which is going to be 3 and 0 go away, 0 and 1 go away, and we're going to be left with minus 1. Whew. All right, so that means that this value here is going to be this value, let's write it up the top, it's going to be E3 on pi, and this value here is going to be this value here, so it's going to be negative 1. Don't forget you have a negative here. So we're going to end up getting E3 pi, these negatives are going to become a positive, plus 1. And that is our answer. And that's the answer they got in the book. That was a long question, but hopefully you understand conservative vector fields and how to find potential functions and endpoints and the fundamental theorem of line calculus. It's been a long journey, but it's time to say goodbye.